Okay, folks. So, welcome to the first talk here. Sven from Bosch will give us the first talk about the Carbyne stack,
yeah.
Open source, cloud-native, secure multi-party computation.
Thank you, Ivan. It's a pleasure to be here. Actually, I never saw that many people interested in MPC in a single room. So my background is not in MPC. I'm actually from the domain of distributed systems. Carbyne stack is at the intersection of both, so there is still a good match. But anyway, I saw on the code of conduct slide that you should be patient with people that have not the same level of experience in MPC as probably all of you do. I'm not. I have a reasonable knowledge level, I would say, but I'm not a deep expert. But I work, as I said, at the intersection of the both topics. So I'm working for Bosch in this nice location that you can see there. It's in South Germany near Stuttgart. It's the research campus of Bosch. As I said, my background is in distributed systems, and I'm one of the maintainers of the Carbyne stack open source project. A few words about Bosch. So we are a big company, so roughly 400,000 employees in 400 plus companies all around the world. We have a dedicated research division where I am working, roughly 2,000 people working there, including PhDs. You may know Bosch as an automotive supplier, but that's only 60% of our revenue source. The others are in energy and building technology, in industrial technology, and consumer goods. So you may know washing machines from Bosch, for example. So we have a very broad set of application domains. Today I will talk about Carbyne stack. That's clear. I will talk about why we started that effort, why we did it in an open source effort, and why we do it at Bosch, which might be not very clear from just looking at it. Then I will give you an overview of what Carbyne stack is. And with that said, I will then shed some light on the future, what we will add to Carbyne stack in terms of functionality in the coming years. So then let's go into it. So privacy preserving computing technologies, that's a fancy term. I don't know if I have to explain it to you, but normally in the context that I work, I have to explain it. So let me say a few words about it. So you can say that privacy preserving computing technologies seal computing environments. And with sealing computing environments, I mean they offer you three basic properties. One is confidentiality. So what you do in a PPCT environment doesn't leave that PPCT without proper authorization. The second one is integrity. So it's protected from alteration, from unauthorized alteration. And the third one is control. So you can say what is allowed to happen on that data. This analogy here on the left is not from me. I saw it. I really don't remember who brought it up first, but I think it's very nice. So this glove box, the dangerous substance in there is the data. That comes with a lot of risks for companies in particular, and you just put your hand through the gloves and then can deal with the data. And it's quite nice. So the glove box is the PPCT. You cannot extract the substance from that glove box or the data from the PPCT. You cannot add something to the box because it's closed. And finally, you also can only do something with the dangerous substance with your hands or with the tools that are available in the glove box. So it's a quite nice analogy, I think. So why do we think that privacy preserving technologies are becoming more and more important? So you don't have to read all of this. It's just kind of should give you an impression that there is a lot of momentum in the thing. So the first observation is that in 2018, when the GDPR has been enacted in the EU, that was kind of a unique thing. First legislation of that kind in the world. But since then, the situation has changed a lot. So now we have in over 70% of the countries of the world, we have privacy or data protection law enacted. And another roughly 9% that have a draft in place already. So that means in a couple of years, we will see the biggest share of the world having strict data privacy regulations in place. So what does this mean for companies like Bosch? So we operate worldwide. So we have to deal with our products and services with all of these regulations. And that creates a lot of effort on our side. And privacy preserving computing technologies are a means of kind of abstracting from the details of all of these regulations with technical means, and thereby reducing the effort that we have to spend in dealing with them. The second observation is that privacy and security are more and more becoming a success factor for companies. So you probably have seen this privacy wars between the big IT companies, but the same applies to the smaller companies. Okay, Bosch is not small, but to other companies as well. We have to deal with customer trust. We have to deal with working with other companies together where sensitive data is shared and processed, and all of this has to be addressed. And privacy preserving computing technologies are very nice technical means of addressing these issues. And finally, you can also look at the big market study companies. So there is growing momentum in this industry. So there is a recent prediction from the Everest Group for the Confidential Computing Consortium that confidential computing will have a market growth year by year of between 40 and 95% in the coming years until 2026. And that means that's 54 billion US dollar market in 2026. So that's a huge opportunity for businesses. And finally, you see that a lot of, at least two major consortia have been created. So the Confidential Computing Consortium, where you can read all the big names of the IT players there, and the MPC Alliance, where Bosch is also a member of, with more startups, but also a few big names like Alibaba, Bosch, and Salesforce. So in the context of that, from our point of view, privacy preserving computing technologies are not only a technical tool, but they are enablers for being compliant, for establishing trust, and for allowing for collaboration with our business partners. So looking into our tool belt, so what do we have in that tool belt? So there are three main classes that we at Bosch at least look into. The first one is computing unencrypted data. So you probably know better than me that this is the, let's say, gold class in terms of security. The unique property is that it keeps data encrypted all the time. Then we have confidential computing. Difference is that in confidential computing, it's memory encrypted, but not encrypted all the time. So when it leaves memory and goes into the processor, it's decrypted and then processed. This opens up the door for attacks on these systems, and we have seen a lot of them in the recent years, but still they raise the bar significantly compared to the state of the art. And finally, so these two first classes are kind of protecting data while being used, but at some point in time, data has to leave these systems to have an impact in the world. And then we have to make sure that from what leaves these systems doesn't allow you to conclude on the data that has been processed in the privacy preserving computing technology environment in the first place. So, and that's the point where statistical disclosure control comes into play. So I'm sure you have heard of differential privacy, for example, or synthetic data generation to replace the original data. So all of these technologies have their pros and cons. We look in particular with Carbyne Stack on computing unencrypted data. As I said, gold standard in security, but there are still some issues in terms of cost efficiency, usability, and maturity that we want to explicitly address with building Carbyne Stack. So what are the use? So why do we do this? This is at Bosch. That's something that I promised to explain. And this is the slide on the use cases that we are looking into. We have two classes. The one is confidential computing use cases and computing unencrypted data use cases. So for confidential computing, just let me explain one of them. We are working a lot with AI pipelines in the context of developing advanced driver assistance systems, where we process a lot of PII. So think of cars driving through the streets and filming everything. And clearly there are people, number plates, and things like that on that footage. And we want to make sure that the risk for the data subjects is as low as possible. And derived from them, then the risk for us as a company is as low as possible. So what we have done in the recent years, we have demonstrated that these technologies can be easily integrated into state-of-the-art AI tools like TensorFlow, like Kubeflow, with very low effort. So since the new generation of, for example, Intel SGX is out, we have nearly no overhead anymore with these technologies. And this creates a lot of external visibility in many signature industry conferences that underpins again that this kind of technology is ready for prime time. For the computing unencrypted data technologies, so the reason why we don't use computing unencrypted data technologies in these use cases is that these systems even bring our infrastructure without encryption to the limit, right? So we cannot add another, I don't know how many factors of overhead to it. But there are other use cases that lend themselves better to computing encrypted data. And there are two of them. Let me explain also one of them. It's called people analytics. So as you have seen on my third slide, I think we are a company with 440 subsidiaries all around the world. And our HR department wants to understand, let's say, the whole picture. What is happening in the subsidiaries, how this compares between subsidiaries, derive knowledge when people, let's say, develop their career through different subsidiaries and so on. And for that, it would be very helpful to pool all that data to do this analytics. And that's exactly what we are looking into with using Carbyne Stack and secure multiparty computation. So one disclaimer, so none of this is in production at the moment. I'm from research. We are looking into that, working together with our business units with the plan to bring this in production, but it's not there yet. So what we want to achieve with Carbyne Stack is we want to allow for enterprise-grade MPC. So to realize these use cases, these are big infrastructures with a lot of things happening in them. So we need this with enterprise-grade capabilities. What does that mean? So you see here a couple of properties that we want to achieve. Scalability is the easiest one. So if you add resources to the system, the capacity of the systems should increase proportionally. Elasticity means that you actually can scale the system with load. We have resiliency, so MPC is a distributed system, and in distributed systems, fault is the normal case. But we have to deal with these failures, and this is the capability of the system is called resiliency. When something goes wrong, we want to understand why it goes wrong, and that requires that we can look into the system, drill deep into the different subsystems and understand what happens. That's called observability. Efficiency is a point. Clearly, we want to have as less cost as possible. Integration, so we don't want to set up a whole new infrastructure for the MPC use cases. We want to reuse what is already there. So that means the MPC solutions must use the same kind of tools as the normal solutions do. Versatility, so we don't want to raise an infrastructure for every use case that we have, but we want to raise it once and then use it for all the different use cases that we have. Simplicity means that operations is a big topic in business. So we want to keep the cost and the complexity of operations as low as possible. And finally, security. Security of the MPC protocols is, of course, an important thing, but in such IT systems, there is also a lot of IT securities, a lot of processes, and we have to make sure that all of this plays together well. So luckily, there is a class of technologies called cloud-native technology that allows for exactly that. You can see that picture here with that many small images here. That's the ecosystem of cloud-native technology. It's technologies that are aspiring or are already a member of the Cloud Native Computing Foundation, and they help you to build, you see the definition there on the right, to build scalable applications, TIC, clouds, which is a elastic environment, TIC, resilient, manageable, observable, all things that have been mentioned on the last slide. It's a shame that there is no security in that definition, but when you look into the different parts of the ecosystem, you clearly see that there are a lot of solutions in there that can deal with security, so that's also covered. And finally, cloud native is pervasive already in the traditional domain in businesses. So integrating an MPC, a cloud native based MPC system into this existing infrastructure should be no big deal. So then the final question of my motivation, why do we do this in an open source context? So I think you can easily imagine that this is a huge effort and we don't want to take that burden on our own alone, but we want to do this with like-minded companies, institutions, and individuals together. So to reduce the cost for us and also share the risk in developing such a thing. Then, of course, we want to leverage the smart minds out there to build these systems with us. It's clear that if you bring the expertise from external people into such a product, you typically improve the quality. Increase trust, so open source means transparency. We think that this is very important for security-related projects because you can, experts from all around the world can look into the code and detect problems early. And the second aspect of this is that we kind of can use this transparency to actually materialize the provable security property of computing on encrypted data technology. So what does it help if I can say, yeah, these protocols that I implement are provably secure, but you cannot have a look at it, sorry. That doesn't make sense. So our approach is it should be open source so that people can have a look. And finally, also for Bosch, it's very vital. You know, the battle for talent is a very nasty one at the moment. With showing to the world that we are working on cool technologies in an open source context helps us in attracting talent. At the moment, Carbyne Stack is a project maintained by Bosch. Means it's more or less ours. We have a community, of course, but that should not be the eventual state of this. What we want to do is we want to transfer this to a foundation so that we establish some neutral ground where people, like-minded people, can work together on the topic. But we are not there yet. We want to first create the respective size of this project to be able to do that. Okay, then coming to Carbyne Stack, I think most of you have already understood that Carbyne Stack boils down to a simple equation. So we combine cloud-native technology, which brings us enterprise-grade processing at scale, with secure multi-party computation, which brings us always encrypted data. And the result is then Carbyne Stack, enterprise-grade, always encrypted data processing at scale. So that's the simple equation behind it. Is this a good idea? We think yes. We have started a couple of years ago already working on this. And there is a recent publication of Gartner that looks into the 12 most important trends for companies that will be success factors in the future. And you see there is privacy enhancing computation, which is just another word for privacy preserving computing technologies. And you see cloud native technologies. And Carbyne Stack is, as I said, exactly a mix of these. So coming a little bit more technical. So what we implement here is MPC in the client server model. You see that figure on the left, just to sort out names. So when we talk about virtual cloud providers, that's an instance of the Carbyne Stack, and in effect is an MPC party. Two or more of them join together to build what we call a virtual cloud. And then you have clients that can interact with that virtual cloud by connecting to the APIs of the individual virtual cloud providers. So as I said, two or more servers, any number of clients. This system can then be deployed in the classical peer-to-peer style, where you actually have each party that contributes has a virtual cloud provider and their own clients talking with that. Or you can deploy it in the offloading scenario, where really you as a client do not care about MPC, let this be done by others. You just interact with the system in a typical client server style. Why we designed that in this way? Because we think operating a virtual cloud provider requires a lot of expertise, and you should rather leave that to people who understand the business. And finally, the clients can be dynamic. They can join and leave at every point in time. And we also support devices that have limited resources. So from a trust model point of view, we support active security in the malicious majority model. So in the discussions with our partners internally and externally, the passive security model for most was not too convincing. So we decided to support the active security model despite the additional overhead that with which it comes. And yeah, it's also attractive from a kind of thinking point of view about trust. So when you deploy it in the peer-to-peer model, you only have to trust yourself, nobody else. And if you deploy it in the client server model, you only have to trust a single VCP in that virtual cloud. So also very attractive from a trust point of view. We implement as an execution model the online, offline, or pre-processing model, simply because these are the most efficient as of today for this trust model. In addition, it comes with a couple of benefits. So you can adapt easily to different load profiles because you can scale offline and online phase independently. So you could, for example, when you think about an automotive use case where cars are driving through the cities, you can create the tuples by night and then using it during the day when there is a lot of actual traffic on the system. And finally, it allows also to use a special kind of hardware offered by public cloud providers today, which is called spot instances. So they are very cheap, but they can be taken away at any time. So by separating data-dependent online phase from data-independent offline phase, we can use this cheap resources for the offline phase. So then looking at the architecture, so what we are talking today is this red box, the Carbyne Stack Foundation services. This include services for computing and for storing data. And on top of that, in the coming years, we want to build data analytics and federated learning systems to support the use cases that I have shown you before. So with this kind of generic layer of functionality, we add this versatility that I said is important in the business context, so that we can support many different use cases using the platform. And then, as I said, we are building on cloud-native technology, and these are the three most important that you can see at the bottom that we use. So Kubernetes, Knative, Istio. I explain quickly what these are and what they do in the context of our system. So Kubernetes is a container orchestrator, so you can deploy on Kubernetes containerized workloads. It's super scalable, so the latest version of Kubernetes allows for systems of up to 5,000 nodes, and on each node you can run tens to hundreds of containers. So this basically should solve any requirement that you have to expect, maybe from weather simulation or something like that. That doesn't really play a role here. And then it's self-healing. So as I said, distributed systems are fault by default, meaning the system has to be able to cope with failures in the system. And that's exactly what Kubernetes can do. It can monitor all the pods running on the different nodes, and if something fails, it automatically takes care that these pods are rescheduled again, and things get solved again. Then on top of Kubernetes, we deploy Knative to implement serverless MPC. So that means you as a developer, as an MPC user, can focus on your code and don't have to care a lot about how you deploy that, because the Knative system allows you to simply take your container that contains the MPC program and then launches it automatically, takes care of monitoring the load on your system, scales up containers accordingly or scales down if no load is there at the moment. So very, very nice and convenient computing model. And finally, there is Istio. Istio is a service mesh. It's about communication. So it allows you to transparently encrypt all the communication channels in your system. This means north-south traffic, so meaning requests coming from the outside to your system, and also east-west traffic, so the communication between your services, because you deploy this on clouds, right? So you do not trust necessarily the infrastructure anymore, so you have to encrypt everything. It allows for load balancing, so Kubernetes can scale up and down as you need, and Istio takes care that the incoming load is distributed according to your specifications to this nodes. And finally, we have observability. So MPC is a lot about communication, so you know how much is communicated in the offline phase, for example, and we want to understand what happens on the network layer in the system. And Istio allows you to have a very detailed picture on what happens in your virtual cloud provider then. Okay, now zooming into that red box, so what is in there? We have 4 services there, 2 for the offline phase at the bottom, 2 for the online phase at the top. Let's start with the offline phase. There is a service called Klishko that actually implements the correlated randomness generation. We are currently incubating this service. It's experimental in Carbyne Stack, but what it basically allows is we have an interface called the Klishko integration interface, and you can easily integrate existing offline phase implementations into that service. This data is then, after generated or when being generated, transferred into a second service, which is called Castor. That is a store for correlated randomness. So all the tuples that are generated in Klishko are then transferred to Castor for later consumption in the online phase. So this allows us for doing this decoupling that I talked before between phases of between offline and online phase to support dynamic load profiles on the system. Okay, I see some strange things here. Okay, then I have to use this one. On online layer, we have also two services. The first one is Amphora, that's the secret store. So basically the clients in our system do the secret sharing and then upload their secret shares to the instances of Amphora in the different virtual cloud providers. So we use additive secret sharing here. The secrets, like in a normal object store, can be tagged with strings or other data types, and then you can, when you retrieve them, you can use this tags to fetch all the data that you want to use as an input, for example, for a computation. We implement the secure and up and download protocols that are required in the client server model in Amphora to make sure that the system is secure. And the final service is then Ephemeral. That's the serverless MPC service that I talked about already. So we use here MP Speeds. Marcel, we will also hear a talk from you on MP Speeds. We have integrated it with Knative, as I said, to support this scalability. At the beginning of a program, you can read inputs from Amphora, and the result can be written again then at the end of the computation back into Amphora for then being retrieved by the clients, for example. And all of this is implemented as containerized microservices to be easily deployed on Kubernetes and support all these nice features of Kubernetes. And in addition, we have clients that you can use to talk to the virtual cloud. For each of the services, there is a client. At the moment, this is implemented in Java, and there is a CLI, like you know from other cloud providers, that you can use to interact with all of the services of Carbyne. So how this works together then? So in the first step, two or more virtual cloud providers come together. They join into a binding process where they create keys, for example, for the offline phase and exchange those keys. When that is done, the Klishko services kick in, start communicating, executing the offline phase, generating the tuples. These are stored then in Castor for later consumption. Then the clients can register with the virtual cloud and the virtual cloud providers. This is done independently, so they register on the one and on the other, not the same credentials. That would be not good, because then one provider could kind of impersonate for the other provider. After registered, they can start invoking services on Carbyne Stack. So that means they can upload secrets, they can trigger ephemeral executions. The ephemeral execution can take inputs from Amphora, as I said, and write results back. And it consumes correlated randomness from Castor while doing that. Okay, so let's look how this works. This is now using the Carbyne Stack command line interface. So this is, we rephrased it to the Billionaires problem because people are richer nowadays. This shows how this is solved the Carbyne Stack way. So first of all, you kind of create the secrets. That CS is the Carbyne Stack command line tool. Amphora is the service that you want to address. Create secret is the command that you want to be executed by the service. And the last value, this 177, is the value that you want to create as a secret in Carbyne Stack. And then, as I said, you can attach text to these values. If you then fetch the just created secrets again using the get secrets command, you see that each of the secrets have get assigned a unique ID. That's a UUID that can be used to identify the secret when used, for example, as an input to a computation. And you see that there are the tags that have been attached, the one that have been provided by the users, and a couple of others that are generated by the system. In the next step, you would write your MPC program. That's again done in MP Speeds Python. There is only these 4 lines in the middle are the actual logic. So you take the first input, the second input, just do the comparison, and the prologue and the epilogue is just for interfacing with Amphora to fetch the data from Amphora and write it back. So this program expects 2 inputs, uses that for the computation, and writes out 1 input to Amphora again. And that's how you invoke the ephemeral service. So you call again our Carbyne Stack command line interface, this time with ephemeral as the target service, and the execute command. And you provide, so we use a special container here, a special Knative application container that is able to compile every program that you give it to it on the fly before executing it. And that is done using that cat command at the beginning. So we take the program, pipe it into the command. The ephemeral services compile the program and start the execution. The I parameters here are the inputs that we want to use. So you see that we use these secrets from Elon and the secret from Jeff as the input. And then the rest of it is just extracting the ID of the output object that has been created. And you can then, as the last step, you can again use the get secret command of Amphora with the result ID that we have just extracted from the execution to fetch the result, which is a 0, which means that Jeff's amount of money is not bigger than the amount of Elon's. Okay, so that's the high-level overview of what we can do today with Carbyne Stack. So what's next on our roadmap? So first of all, I said that cost is, of course, an issue for us as a business. And if you look deeper into it, when you deploy these systems to the cloud, it is the bandwidth that dominates the cost by a large factor. So our primary goal is to reduce the offline costs, and we have seen in recent months and years promising approaches like pseudo-random correlation generators to bring this communication overhead down significantly. And this, based on the assumptions that are made in the respective papers, would allow us to bring down the cost of using MPC in the cloud across different clouds by 3 orders of magnitude. So that's really significant money. So right, $10,000 a day versus $10 a day. So it's a real difference, right? The second thing that we will work on is, as I said, provide these higher level services to support the use cases that we have in mind. So the plan is to come up with a database management system that is MPC based on top of Carbyne Stack, where you can use SQL to query that system for results, for data. And the second one is we want to establish a federated learning system that does secure aggregation on top of Carbyne Stack for use cases. I've not described it, so sorry for that. I cannot refer to that now. But it's relevant for us when we work, for example, with OEMs, so the automotive manufacturers together. They are hesitant in giving us the data because you can read a lot of internal information from the data that shouldn't be shared. And with tools like federated learning, you can convince them to still share that data because they don't have to care a lot about the privacy or the confidentiality of the data. Then we will invest time into implementing authentication and authorization. So who is allowed to do what in the virtual cloud? So there are 2 great tools available in the cloud native ecosystem called Open Policy Agent and DEX. So Open Policy Agent allows us to define very flexible policies for authorization, and DEX allows us to integrate basically every OpenID Connect system as an authentication mechanism to the system. So this will allow us then in the end, for example, to say that user Bob is allowed to fetch all secrets that have been tagged with a specific tag T. And this is then evaluated by that policy, and the decision is made that this is okay to do. And a second example could be you can define very flexibly that everybody who has provided an input to a computation has also access to the output of the computation in Amphora. Things like that could be very easily then specified by the end user of the system. Then observability is a big issue for us. There is a nice tool called Prometheus that allows you to instrument your microservices, and they then publish all the data that you are interested in to a central service that can also be visualized using a dashboard and so on. So things like function f of user Bob has been invoked 200 times in the last 10 minutes or something like that. Or more importantly at the moment, so Klishko, our offline generation service, must to kind of know how many tuples are available in Castor and then trigger generation of new tuples based on the requirements from the computation. And with Prometheus, you could easily say, please give me the tuple consumption rate for multiplication triples over the last hour, and then Klishko can make the right decisions of what tuples to create next at what rate. There's a slide missing, no problem. So let me summarize first by telling you how, if you are interested in how you can engage with us and collaborate with us. So there is this nice onion model of open source project. So you start at the outer layer of this onion as a watcher. So that is where you should be today then. You can follow our LinkedIn feed, for example, or visit our website regularly to see what is going on with Carbyne Stack. Ideally, you would then at some point in time become a user. So download the system, deploy it on your premises or in the cloud, use it, ask questions, discuss with us, report issues, all of the things that help you in working with the system and help us in developing it further. Then ideally, you will find some features missing and become a contributor. So implementing the things on your own, contribute it to the open source project, includes testing, of course, and adhering to the different policies that we have in the project. But contributions are always welcome. And we, as the maintainers at the moment, Bosch, we are very happy to review these contributions and teach you in how to contribute to Carbyne Stack so that we can actually accept it. You can use for this inner layers of the onion, you can use GitHub. We have an organization for Carbyne Stack where all the code is deployed. We have compliant images. So that's, by the way, a big issue for companies. You are allowed to just upload a Docker image somewhere. You have to make sure that you comply with all the open source regulations. That's really a lot of effort that comes with it. Was a little bit unexpected for us as well, but yeah, now it's done. So these images are compliant. So you should be able to use it in a compliant way. And finally, there is a Discord community server where you can interact with us, ask questions, and so on. Okay, so with that said, let me summarize. So I hope that it became clear that PPCTs are a big thing for us as Bosch and also in the world, because they have a huge business potential and also a huge potential for mitigating risks. With Carbyne Stack, we want to lift MPC into the cloud so that it can be deployed to cloud systems and can be used to cloud systems and can use it in enterprise-grade quality for our use cases. Credits go to the Carbyne Stack community, so it's not only Bosch, Honda Research joined our project recently and have contributed already a lot. So, for example, initially we only had support for 2 parties. They implemented support for any number of parties now that's available. UTS, University of Technology Sydney, is joining us in implementing the secure offline phases or improve their efficiency. Special thanks to all the open source enthusiasts out there that create all the fantastic tools that we are built upon. Special thanks to Marcel and the community of MPCTs for providing that great tool that we are using at the core of Carbyne Stack. So please join us in that effort if you want to. There are already some opportunities out there. So UTS has currently 2 postdoc openings for working on these topics, and we as Bosch always have the option to host interns with us. So with that said, thanks a lot, and I'm open for questions.
Thanks for a great talk. Before we start the questions, let me just say that we are streaming this also via Zoom, and therefore, and also we don't really have, it's not feasible to bring mics to the people who ask questions. So you have to shout, and then please, if you could repeat the question then, so that the people on Zoom can also hear the question, because they won't be able to otherwise. Okay, questions? Yes? Oh.
Thanks very much for the talk. This is a very massive and interesting undertaking. Do you have an estimate how many person months went into building all of that, integrating all those cloud technologies with the speeds and all this?
Yep. So the question was what the effort is and was that went into this massive effort. There is not really an estimate. So we have worked on this as a side project for a couple of years now, Bosch internally, before we decided to go public with it. I would say these are 2 people, maybe a year. Now it's a little bit hard to say because we can't look into, for example, what happens at HRI I can tell you that at the moment, roughly 11 people are working on this, with a soon extension to probably around 60, 70 people. Of course, not all full time, so that would be the wrong expectation, but we are gaining momentum, and the effort that flows into it is increasing. Yeah.
Yes, there was another question. Yeah.
I thank you very much for the talk. My question is more technical. So you have the MPC servers, and who is it that tells them now you have to start computing, like now start connect to each other? I understand it's the client, but in that case, what happens if the client doesn't start all of them, or if you have multiple clients that each have to provide input? How do they know when they can start?
Okay, so the question was, how do the MPC servers or our virtual cloud providers know when they, for example, have to start an execution? So I understand that question as how the coordination is happening, right? So initially we started out thinking about implementing a kind of consensus mechanism at the bottom, but that's not there yet. It is for Klishko. There we use etcd, that's a coordination service from the cloud native world to coordinate actions in the distributed systems, let's say it this way. And for Klishko, we do it using etcd. So, but for the other services, you're right. So if the client misses to invoke, for example, the execution trigger on one of the virtual clouds, then simply the other one starts it and waits indefinitely or until a timeout, until it knows that, yeah, it failed. Yeah. So it's the responsibility of the client at the moment.
Okay, we have two.
Yeah, thanks for the very interesting talk. I was just wondering, what exactly, how do you see this being used in the future? Is this like a service you're going to sell to different companies, or is it going to be used like internally within Bosch and collaborators?
So the question was what our plans are in using Carbyne Stack, if I understood correctly, as Bosch. So at the moment, we are piloting in public funded projects several applications. So this human resources use case is one of them. And that means that we are at the moment only have plans to use it internally. We also are in active interaction with bigger initiatives like Athena X. That's kind of a big initiative building a backbone for data exchange within the automotive domain. And we try to push Carbyne Stack as kind of the foundation for this backbone. But that would be an external use. Yeah, this is ongoing, so nothing decided yet.
We have there, yes.
So as I understand, you're currently using MP speeds as the sort of basis, including, I'm assuming, the compiler in MP speeds. Do you have plans to sort of make a fork of this at some point, or enhance it and upstream it to MP speeds, or what's your plan?
Yeah, so we actually made already some contributions to MP speeds for things that we needed in Carbyne Stack. The plan is not to fork this, at least we have no active plans of this. What we of course are interested in is kind of bringing this enterprise grade aspects also down to the layer of the MPC engine. We have to see how this can work out. Yeah, but no plans at the moment to fork it. Yeah.
Okay, there was someone here. Yes.
Thank you for the great talk. I was wondering if there are any limits on how long the protocols can run and how you deal with failures in the online phase. For example, if one of the VCPs goes down in competition.
Yes.
Yeah, so sorry. The question was, how do we deal with failure in the online phase, for example, and how long computations can in principle run? So the answer to this is that it's configurable. So you can configure Knative how much time you and resources you as a user might be able to spend for a certain computation. As soon as these limits are hit, the container is forcibly shut down by Knative. Yeah, so it depends on how the operator of a Carbyne Stack virtual cloud provider wants to set the system up. And dealing with failure, so if it fails, then the client gets a response that HTTP response that the execution has failed with the respective status code.
Jack?
A little lower level question, maybe. When you think of composability from the crypto composability if you run protocol today, then maybe in a month I would want to look at some of the messages that went around and prove something about them in a workflow that hadn't been thought of yet. Is there any log service that would, after the fact, go and get me the transcript of an execution that happened in the past?
Yep. So the question was how we deal with composability in the crypto sense, and whether there are any sources of information to get the transcript if you decide then later on to run another execution on top of the previously generated data, right? That was the. So our way of dealing with this is that we currently use that capability of speeds to kind of being able to have this reactive kind of protocol, so reusing the results from one run in another one. Regarding the transcripts, that's not available today. We might decide to provide that when we integrated observability tools. So there are also not only monitoring tools, but also log service tools where you can collect all the logs from all the nodes in your system and centralize them. So maybe that's might be an option to integrate that aspect into the system.
Okay, we are close to being out of time, but
do you have any examples of what was this applied to, or things could be applied to?
So the question is whether we have some examples of where this could be applied to. So first answer to the question is there is a tutorial online on our website where you can have a look at how this Billionaires problem is executed, and also machine learning use case. And the other one is what I presented you on the use case slides, right? This human resources use case.
Specific examples, you know, like it can apply to specific applications, or you wouldn't know.
I do not get a question. So
people that have used it in a specific setting.
So you mean Carbyne, whether Carbyne Stack has been used already in a specific setting? No, so we open sourced this in September last year, so quite young project. It's also not ready for prime time, to be very honest. So expect a lot of failures, missing features, and so on. So we are not there yet. But the plan is to be there, and it will take some time until we're there. So if you think about open source projects that start from scratch, you typically have to think of years until this becomes applicable in a productive setting. So patience.
I think the only reason that they called it the Billionaires problem was that because the protocol was linear, the number of values. When we don't want to go to billionaires, actually want to go down. The number of people.
okay, so you can actually be too rich to do cryptography.
Yeah.
Last question. We have time for? We are out of questions. Oh, there's one there. Yeah.
So, I don't know if I missed anything, but I have the impression that the target infrastructure for Carbyne Stack is one enterprise, let's say Kubernetes cluster. Is it possible for two Carbyne Stacks to kind of handshake each other and run fast computation among, for example, different institutions?
So the question was whether Carbyne Stack can be not only deployed to a single Kubernetes cluster, but also to several. The answer is yes, it is supported, and that's actually also the targets that we have. Deploying it on the same Kubernetes infrastructure doesn't make a lot of sense. Typically, you would deploy it on different Kubernetes cluster, ideally also running on different public cloud providers, or at least in different regions of the same public cloud provider, to get that, first of all, operational independence, to give you the uptime guarantees and so on, but more important, to give you the promises that MPC give you, right? If you have as a protection goal that the cloud provider itself should not be able to look into the data, then you have to distribute it over several cloud providers. So yes, that's supported, yeah. Yes. Okay, thank you.
Thanks, Sven, again.